Hey friends, today I'm going to show you a few basic definitions of linear algebra. So, this is the formal definition of a group, and while it's a bit long, I'll take you through it step by step. So, a group is a set G of elements with an internal binary operation. And now, this is just some symbolics. This is the symbol we will use for the operation. We'll see it a lot in the rest of the definition. I'll just call it star from here on out. And then it comes with an input and an output. Now this just means that there are two inputs and both of them are in G, and this is the output and it's part of G. So it's simple really. And it comes with the following characteristics. So the first one is that for all elements A, B, and C in G, we have parentheses A star B, parentheses star C, equals A star parentheses B star C parentheses, which is the associative law. And basically what this just means is it doesn't matter if you use the operation on A and B and then use it on C, or if you use it on B and C first and then use it on A, it doesn't matter, you'll still get the same result. And the second law is that there exists a neutral element, E, which is part of G, and basically this symbol just means that the element is part of G, for which we have the following: E star A equals A star E equals A. So it just means that if you use the star operation on E and A, it will just be A. For all A, that is part of G. And now the final law is that for all A that is part of G, there exists an inverse A that is part of G with this. And now this A to the power of -1, that's just the symbolic for it. You don't actually take it to the power of -1, but it just means that it's the inverse of the element A. And the law is that A star inverse A equals inverse A star A, which is the neutral element that we saw in law 2. And this is just called the existence of an inverse element, and that's the formal definition of a group. Now I'll also show a quick example just to show what this is like, and we'll take a pretty easy example, the real numbers, and we'll show how these three laws hold in the real numbers. Now we'll begin with the associative law, and for each of these statements there will be different cases for addition and multiplication, so we'll go through them separately. Let's begin with addition. We'll just take any three numbers out of the real numbers. Let's take 3, 6, and 2. And now we add these two numbers first. And then in the second case, we will add the last two numbers first. So if they equal the same result, then we know that rule 1 holds for addition. So we'll begin with the first example. 3 plus 6 equals 9, plus 2 equals 11, and 6 plus 2 equals 8, so 3 plus 8 equals 11. So these are equal to one another, and with that, the associative law holds for addition. We'll continue with multiplication. We can use the same three numbers, 3 times 6 times 2. And then here we'll multiply the first two numbers first, and in the second case we'll multiply the last two numbers first. And here in the first case, 3 times 6 equals 18, times 2 equals 36. And we multiply 6 times 2 in the second case. We have 3 times 12 and 36. And we see that these are equal to one another. So with that, the associative law holds for addition and multiplication. Now for the neutral elements, we can see for addition it's 0, because if we take any number A and add 0 to it, it's still A. And the same for the other way around. 0 plus A equals A. So we can see that 0 is the neutral element of addition. Now for multiplication, it's 1, because 1 times a equals a, and a times 1 equals a. Pretty simple. So 1 is the neutral element of multiplication. Now it's time for the inverse element. For addition, we will want to get the neutral element when we do all of the computing work. So we want to get 0, and we start with the number a. And it's pretty easy to see that the inverse element for any a in the real numbers is negative a, because a plus negative a, or a minus a, is 0, and it's the same for the other way around. Negative a plus a equals 0. Now for multiplication, we will want to get 1, because that's the inverse element, the neutral element, and we'll take a number a, and then if we multiply by something, we want to get 1, and we can also easily see that the number we use here is 1 over a, because that equals a over a, and that's just 1. So this was just a quick example for the real numbers to show how this comes into play. So this is the formal definition of a field, and I'll again take you through it step by step. Now the formal definition is this: a field is a set K with two inner binary operations, plus and times, which is just the plus and times that you already know, with the following characteristics. And the first one, that K, this notation just means that it's K combined with this operation. So K combined with the operation plus is an abelian group. And now what this means is that it's a group, which is the definition I just showed you, plus the abelian part, which just basically means that if you take two elements out of this group, then it equals this. So you take A and B out of this group, then A times B equals B times A. So that's basically all it means. It features the commutative property. And now the second part is that the group K, or the set K combined with the times operation, is also an abelian group. So you know what that is. And the third part is that the distributive properties are fulfilled. So if you take A, B, and C out of the set K, then you have these properties, which I'm sure you know. A times B plus C in parentheses is A times B plus A times C, and A plus B in parentheses times C is A times C plus B times C. And that's basically all there is to the definition of the field. And another thing, with having these two operations, plus and times, you also fulfill the definition of minus and division. Because if you want minus, then you just need to do plus minus another element. So if you want to take 5 minus 3, for example, then you would take 5 plus, which we have already, plus negative 3. And that then equals 2. And for the dividing by, it's basically if you want to take 5 and divide it by 2, then that's the same as multiplying by 1/2, which is 2.5. So yeah, that's the definition of a field. Now, as another quick example, I'll use the real numbers again, just to show that these characteristics hold. Now first, we start with the abelian group. We've already shown the group part, that these sets fulfill all of the group properties. I've already shown that in the last example. Now to the abelian part. So for addition, it just means that A plus B equals B plus A. we can see pretty easily that 6 plus 3, we'll just take 6 and 3 as example numbers, equals 3 plus 6, which equals 9. So yeah, that's pretty simple there. And for multiplication, it would mean that a times b equals b times a, which would then mean, if we take 6 and 3 again, 6 times 3 equals 3 times 6, which equals 18. So we can see that this also holds for multiplication. And now we need to show that the distributive properties are fulfilled. So we'll take 3, 6, and 2 as in the last example. And we want to see if 3 times 6 plus 2 equals 3 times 6 plus 3 times 2. So does this hold? Well, on the left side, we have 3 times 6 plus 2, so solving inside the parentheses, we get 3 times 8, that equals 24. And now on the right side, we have 3 times 6, which is 18, plus 3 times 2, which is 6, and that equals 24. And these two equal each other, so we've proven that. And now we'll use 3, 6, and 2 again for the second distributive property. So is 3 plus 6 times 2 equal to 3 times 2 plus 6 times 2? Well, let's find out. 3 plus 6 equals 9 times 2 equals 18. And on the right side, we have 3 times 2, 6 plus 6 times 2, that's 12, and that's also 18. So these two equal each other, and this holds. So that was just another quick example to show that R is a field. So you've now learned the basic definitions of a group and a field. I hope you enjoyed and understood and learned something, and I'll see you next time. Bye!